The aim of this investigation was to develop an experiment that made a measurement of the acceleration due to gravity. This could be done through several methods. However, for our experiment, we decided to drop a ball and record how long it took to fall with reference to a meter ruler. We assumed that through this, we could approximate the acceleration due to gravity on the ball by taking two intervals from the ball's drop and calculating the change in velocity over time. This should supposedly generate some acceleration value near the actual value of the acceleration due to gravity, which is 9.8 meters per second squared. The experiment was set up as shown here, with a retort stand to hold the ball, a meter ruler placed vertically upwards next to this retort stand, and another retort stand to hold the camera phone placed relatively 50 centimeters away. The camera phone was then turned on to record the ball drop, and the adjustable knob on the clasp holding the ball was loosened until the ball fell. This was done rather than a group member dropping the ball to avoid any extra force and/or uncertainty. To derive the acceleration due to gravity from the video, the first half of the video was taken. From this interval, the initial position of the ball in reference to the meter ruler was recorded, which in this case was 38.2 centimeters, and the final position of the ball recorded was 31.45 centimeters. The difference between the two positions is negative 6.75 centimeters or negative 0.0675 meters. Since velocity is change in displacement over change in time, the time it took for the ball to travel this distance in the video is required to be converted to real time, or 30 frames per second. Since the camera records in 240 frames per second, the time it took for the ball's displacement, which was approximately 0.2 seconds, needs to be multiplied by 1/8 to give 0.025 seconds. The resulting velocity is negative 2.7 meters per second, which we will denote as our initial velocity. From the second half or interval of the video, the initial position recorded was 31.45 centimeters and the final position was 23.55 centimeters. The displacement is then negative 7.79 centimeters or negative 0.079 meters. Since the intervals were taken as halves of the video, the time it took for this displacement would be the same as the first interval, meaning the resulting velocity would be negative 3.16 meters per second, which is our final velocity. Since we now have both the initial and final velocities, as well as the time it took for both, the acceleration due to gravity can be derived. Acceleration is described as the change in velocity over the change in time. The change in velocity will be the final velocity, negative 3.16 meters per second, minus the initial velocity, negative 2.7 meters per second, which is negative 0.46 meters per second. The time it took can be calculated by adding the two times it took for each interval, which is 0.05 seconds. The acceleration is then calculated to be negative 9.2 meters per second squared. So there are two random errors that must be taken into account for the calculations of the acceleration. Since the ruler's smallest increment is 1 millimeter, we can take half of this and say that the error in reading measurements is plus or minus 0.5 millimeters. The second error is within the time measurements, and the uncertainty in this is half the smallest measurement of one frame, which is half of 0.005, making the uncertainty plus or minus 0.0025 seconds. Following the rules of uncertainty calculations, the acceleration is negative 9.2 meters per second squared plus or minus 3.013 meters per second squared. The value we arrived at for the acceleration, negative 9.2 meters per second squared, is relatively close to the actual value of the acceleration due to gravity. The reason why the value is negative is because the force of gravity is always acting downwards, and if measurements taken upwards are defined to be positive, the downward force of gravity is negative. The downward force of gravity means all objects when dropped from a height fall towards the Earth. To improve the experiment, a video tracking software program should be used to derive a more precise value of the acceleration due to gravity, instead of manually attempting to take recordings. This manual process is most likely what led to the inconsistency with the real value. The range in the change of velocity should also be increased by dropping the object from a higher vertical distance. To ensure the experiment is a fair test, several trials of the ball drop should be carried out. In conclusion, the experiment was fairly successful in measuring the acceleration due to gravity. The value of the acceleration from the experiment was negative 9.2 meters per second squared, which is relatively close to the real value, which is 9.8 meters per second squared, although there was an uncertainty of plus or minus 3.013 meters per second squared. This fundamentally means that the downward force of gravity and its acceleration can simply be approximated through dropping an object and observing how long it takes to fall.